Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's easy level puzzle. And it's take that easiness with a grain of salt because it's considered easy by the people on the Logic Masters Germany forum, and there's a lot of really smart people there. Today's puzzle is called Sandwich Break by Yitrio, and here are the rules. We have normal Sudoku rules apply, which means in every cell in the grid, place a single digit such that every row, column, and designated 9-cell region contains the digits 1 through 9 exactly once each. We have yin-yang shading, where we need to shade some cells such that all shaded cells are orthogonally connected, and all unshaded cells are orthogonally connected, and no 2x2 area is fully shaded or fully unshaded. So here's an example of a valid yin-yang shading, because what does it mean to be orthogonally connected? It means as a region, you can go from any cell in the region to any other cell in the region just by going through edges, all while staying within the region. So for example, to get from this cell to this cell here, you can go through these edges, all while staying within the region to get to that cell. Same with the unshaded region. In the unshaded region, you can go from this cell to this cell just by going through edges, all while staying within the region. This is not a valid yin-yang shading because to get these cells now cannot go to these cells out here unless they go through a corner or they go outside of the region through an edge, neither of which is allowed. And this is not a valid shading because we have a 2x2 area that is fully shaded. This is not a valid yin-yang shading because this would be a 2x2 area that is fully unshaded, which is not allowed. We have numbers outside the grid are yin-yang sandwich clues, where they give the sum of the digits in unshaded cells in that row or column that are between the outermost shaded cells of the row/column. Note that there will always be at least 2 shaded cells in every row and column that contains a clue. Interesting. So, if we were to use this shading as an example, it's probably not going to be valid. But the digits between the outermost we have to give the sum of the digits in unshaded cells in the row or column. Between the outermost shaded cells of the row or column. And there always has to be at least 2 shaded cells in every row and column that contains a clue. So this actually doesn't work at all because of the shading, because there's no unshaded digits, unshaded cells between these outermost shaded cells. I guess let's do this. This would have to mean that the shaded cells between these 2 cells must add up to 11. So these 4 digits would have to add up to 11. So then you would have to have 1, 2, 3, 5 here to add up to 11 as that. But obviously we run into problems with some of the other sums. But basically, the number outside the grid is the sum of the digits in unshaded cells that are between the outermost shaded cells in the row or column, respectively. And again, you always have, in a row or column with a clue, you always have guaranteed 2 shaded cells at least, which the unshaded cells must be between. Anyways, those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's go. Okay, to add up to 42, and since two cells are shaded, that would mean the rest must be unshaded. So these are guaranteed to be unshaded, and this has to be a 1-2 pair here. Same with row 8. To add up to 41, that means you're missing two cells. These have to both be blue, and it has to be 1 and 3. Well, to add up to 35 here, the outermost you can have 5 digits. And the thing is about yin-yang shading, once you swap shadings, you can only swap back one more time. And you don't have to have this. So on the edge of the grid, this is on the edge of the grid, apologies. On the edge of the grid, you either have 0 changes of color or you have 2 changes of color. You can't have 4 because if you had 4, so say this went blue, green here, blue here, swap to green here. How do you orthogonally connect the green region without breaking the blue region into 2 segments? You can't. So that's why you can't have more than 2 changes of shading in a region. Well, we know 35 is a sum of the unshaded cells in the region, so it cannot be sort of sprinkled out throughout here. It has to be one continuous set, and then we have to have blue on the outside. So this must then be 5 greens, because that's the minimum number of cells that add up to 35, and then this has to be blue, which means these have to be blue out here to be orthogonal, because again, you can only change at most twice on the edge of the grid. So these are all blue. This has to be green because of the 2x2 area around it. These add up to 11 in the unshaded cells. This is 2x2, that's all green, so this must be blue. This is 2x2 cell, that's all blue, so this must be green. 2x2 area, that's all green, so this must be blue. Same with that, green and blue. So these must add up to 1, 2, 3, and 5 to add up to 11 for 4 unique digits. Okay, this cannot be 1 or 3 because of the 1, 3 pair in the row already. This must have, so we have 3 greens here. This can't be green, it's blue. We have at most 2 greens in this row because the outside ones are blue. Oh, to add up to 38. So this has to be 5 through 9 here to add up to 35, which leaves 1 through 4 in the remaining digits in the row 1. This can't be 1, 2, 3, or 5 because of the 4 digits adding up to 11 here. This can't be 1, 2, 3, so this must be 4, which means 4 cannot be here, 4 cannot be here. Remaining digits in column 2 are 6 through 9. Okay. We have 2 digits here. You can have at most 3, so you have to have 6 unshaded cells, green cells in row 6 to add up to 38. But we don't know if all of them are green, right? We know also in yin-yang shading, if you have 2 diagonals that are the same color, the other diagonal has to be one of the same color and one of the different color. Because if you try to have these be both green, obviously you have a 2x2 area that's all green, which is not allowed. If you try to have them both blue, how do you orthogonally connect the blue without basically breaking the green into multiple regions? You can't, and the same thing with the green. So this must be green here. Between the blue cells is at least 3 green digits. Oh, and this is blue, blue. We have 3 greens here, so this must be blue here. We could have 4 blue greens here. That is possible. We need at least 2 more, though. We can't have all 3 green. If these were all 3 green, the problem is this 2x2 area would be all green. So we have to have at least 1 blue. We can't have just 1 green between these blues. We can't have just 2 greens between these blues. So we cannot have blue here and blue here. So say we had this as green. If this is green, that forces this to be blue and blue to be it because of the 2x2 areas. But then the problem is this is never adding up to 24 with 2 green cells between the outermost blue cells. So this has to be blue then, which forces this to be green and this to be green to add up to 24. And this must be 7, 8, and 9, adding up between the outermost blue cells, which eliminates 7, 8, and 9 in the rest of the column. Okay. These are 3 greens, so this can't be green here. It's blue. This is a blue diagonal, so this can't be green, green. It must be blue there. We have at most 2 green cells here between these cells. Okay. This is either 1, 2, or 3 here, because the green cells between these 2 cells must add up to 3. So it's either 2 of them with the 1 and 2, or 1 digit that's 3. Either way, in this box 7, we have 1, 2, 3 as a triplet, which eliminates 1, 2, 3 in the rest of the column of the box. This can't be 2, it's 5, which eliminates 5 in the rest of the box. Now we have a 1, 2, 3 triplet in box 1. So the rest of the digits in box 1 are 5 through 9. Interesting. This is 3 digits here, 3 digits here. We have a 1, 2, 1, 2 pair in column 3, which eliminates 1 and 2 in the rest of the column. This can't be 1 or 2. It's 3, which makes this 1, which makes that 2, which makes that 1. So no 1 here. No 1 here. This is 3, and it's the only 3 in row 7 that must be green. So the rest must be blue. So this is all blue. This must be 38. We could have another. This is, okay, this digit, this is 1, which makes this 3. This cannot be a 1, 3 pair adding up to 4 here between the 2 blues, because of this can't be 1 or 3. So this must be 4. And the rest of the column then must be all blue to be in between the 4. That means we have 6 digits, which must be green to add up to 38. And it has to be the digits that are not in the green have to be add up to 7, which is 45 minus 38. So that's 1, 2, 4. So then this is 2 or 4. This is 1 or 2. This is 1, 2, or 4 here. 3 eliminates 3 here, so that's 2, which makes this 3. That means this can't be 3 here. It's 2. Which eliminates 2 here as a 2 pair. We have 1, 2, 4 as a triplet in row 6, which eliminates 1, 2, 4 in the rest of the row. This can't be 1, it's 3, which makes that 1. This can't be 2 because of 2 in the column. These must orthogonally connect somehow. Where's 4 in box 7? Can't be here, can't be here, so it has to be one of these 2, which means this can't be 4, it's 2, which makes this 1, which makes that 4. Okay. To add up to 24. So the remaining digits in column 4 are 1 through 6. No 4s here because of 4 in the box. No 3, no 2, no 1 here because of 1 in the box, 3 in the row, and 2 in the row. No 2 here. This is 1 and 4. Okay. This is 5 through 9 here. 5 through 9 here. Where is 4? 4 has to be one of these two digits here. Hmm. So this is 4, that's 25. This is 9 at most, but this could be all... You can't have all blue here. This digit cannot be 1, 2, 3, 4, 5, so it's 6 through 9 here. This is 2, 6 through 9 here. This is definitely between these two digits. So we could have green going all the way down here. This is definitely between two green digits. We are definitely having some greens here. Because, so if this is blue, this would have to be green. But the problem is we'd have 3 greens here, and they do not add up. It would be at minimum 2, 6, and 1. So, okay, say we had a blue here. If we have blue here, that guarantees this is green. One of these has to be a green here, because you have a blue-blue pair here, and if we try to have a blue, we can't have 2 blues here. So that would guarantee one of these is green. We'd have 4 digits here trying to add up to 9, which is impossible. So this cannot be blue. It has to be green here. This is 3 greens here, so this must be blue. Now, can this be blue? There. If we have blue here, this could have to be green. That would be blue. That is possible if this were a 1. Right? You could have 1, 6, and 2 adding up to 9. But we already have a 1 in the row. So that's not possible. So this cannot be blue here. This is green. Can we have blue here? That would be green, green. That's possible. And you could have green, green, green. So, we could have all green here, though, too. So this cannot be 6, 7, or 8 here. It's actually, I guess no. It can't be 6, 7, or 8 here. If this were 6, 7, or 8, that implies there are other greens in this column which add up to 9 with it. But this digit can only be 5 through 9, and it's guaranteed to be between the blues if you have another digit here that adds up to 9. So this cannot be 6, 7, or 8. It's 2 or 9 here. We don't know about this. This is blue. Therefore, these two digits must add up to 7 at least, or at most, and therefore this is 2, 5. Therefore, these are all blue. So these are all blue. This 2 and 5. This can no longer be 5. 2 eliminates 2 here, so that's 9. Which means this can't be 9. No 2 or 9 here. No 9 here. So no 5 here. These are all blue. This is 9 between the blues. This can't be between blues then, so these are green. Interesting. This can't be 9 because of 9 in the column. One of these two has to be a green, at least. This adds up to 23. And we have to have 3 green cells. So this is green, green, green. So this must be 6, 8, and 9. So this cannot be 4. To add up to 23. That eliminates 6, 8, and 9 in the rest of the row. So this can't be 6, 8, and 9. It's 7. This can't be 6. It's 2, 3, 4, 5. No 5 here. No 5 here. This adds up to 17. And this is guaranteed to be a 4. Remaining digits in row 5. Well, this can't be 6, 8, 9, or 7. Cannot be 1, 2, 3, 4, so it has to be 5 here. Which eliminates 5 in the rest of the row. So we have 1, 2, 3, 4 left in the rest of the row. This can't be 2, 3, or 4 because of 2, 3, 4 in the column. So this is 1. This can't be 1 here. No 2 here. No 4 here. That makes that 3. So this can't be 1 or 3 here. This 4 eliminates 4 here. So that's 2, which makes that 4. These 4 digits must add up to 17 with potentially that digit. We don't know. These add up to 25. With one, oh, it's between the blues. So if we had blue here, this would have to be green, green, and that would be too many digits, right? You have, well, yes, too many digits. You'd have 5 digits with 3 of them being 6, 7, or 8 at minimum. So 6, 7, 8 at so this cannot be blue. If this were blue, we'd have to have green be here. It has to orthogonally connect, so that would be green, green. That would be 1, 2 at minimum. Well, actually, it could be 1, 3, and then 6, 7, 8. That actually could work. Hold up. Let's continue with the 17. Where is 2 actually in column 8? It has to be here. So 1, 4, and 2 only add up to 7. And another single digit can only be 9 at most, so we are guaranteed this has to be a green to add up to 17, because we have 1, 4, and 2 only in the row. And that plus 9 only adds up to 16, so that's not, so we need another green. So then this is 1, 2, 3, 4, and 7, which eliminates 7 in the rest of the box. This becomes a 6, 8, 9 pair, which eliminates 6 in the rest of the column. This becomes a 7, 8 pair, which eliminates 7 and 8 in the rest of the row. So this is 6, which eliminates 6 in the rest of the box and column. That leaves this as a 5. We have 6, 8, and 9 remaining in row 4. No 5 here because of 5 in the column. So right now, these guaranteed have to be between a blue. So can you add up to 25 with these? So 3 would have to have 6, 7, and 9 to add up to there. Or you could have a 1 here. Okay. 7 eliminates 7 here. This becomes 7 eliminates 7 here. So this becomes an 8, 9 pair, which eliminates 8 and 9 in the rest of the box. This can't be 8 or 9. It's 6, which eliminates 6 in the rest of the row and column. 8, 9 as a pair eliminates 8, 9 in the rest of the column. So this is 5, 7, which eliminates 5, 7 in the rest of the box. This can't be 7. It's 8, 9. That forces this to be 6 here. So there's no 6 here. Leaving 4, 7 in the remaining digits in column 1. Okay. 4 eliminates 4 in the rest of the column here. No 5 here because of 5 in the column. So either this is green and that's blue, or this is green and that's blue. 7 eliminates 7 here, so this is 8, which makes that 7. 8 eliminates 8 here, so it's 9, which makes that 8. This can't be 8 or 9, it's 6. This can't be 6 or 8, it's 7. This 8, 9 pair eliminates 8 and 9 here, so that's 6. No 6 or 9 here, that's 8. So we have 6, 7, 8, and 3, which only adds up to 24. We need another green in between, so that's green, and this is blue, which makes that a 1 to add up to 25. Right? 6, 7, and 8, 21, plus 1 is 22, plus 3 is 25. That eliminates 1 in the rest of the box. These 3 must add up to 13, so these 2 must add up to 12, because 13 minus 1 is 12. So this is 1, 5, and 7. This can't be 7 because of 7 in the column, so it's 5, which makes that 7, which makes that 5. That eliminates 5 here. No 6, 7, or 8 here. It's 5 or 9. No 5, 6, 7 here because of 5, 6, 7 in the column. So that's 8. No 8 in the rest of the row. So that's 24. So let's count. 2, 1, 3, 5 is 11. 8 eliminates 8 here, so that's 9. That definitely adds up to 42. 7, 8, 9 adds up to 24. 4 adds up to 4. 1, 3, 8, 6, 7 is 12 plus 13, which is 25. 2 and 5 add up to 7. And then 9 adds up to 9. 1, 7, 5 adds up to 13. 1, 4, 7, 3, 2 adds up to 17. 9, 8, 6 adds up to 23. Everything but 1, 2, 4 adds up to 38. This is 3, and everything but 1 and 3 add up to 41. So now the rest of this is just normal Sudoku. Okay. Remaining digits of column 8. We have what? 1, 3, and 4. 3 cannot be either of these digits because of 3 in the box, so 3 has to be there. No 3 or 5 here. It's 6, which makes this 5. No 5 or 6 in the remaining digits in column 4 and box 2. This can't be 5, so it's 9. This can't be 9 or 6. It's 7. This can't be 7 or 9. It's 6. Okay. We have 1 and 4 remaining here in column 8. Column 6 now has 6 cells, so we have to have 2, 4, and 5. This can't be 2 or 5 because of 2 or 5 in the row, so this is 4, which makes this a 2, 5 pair, which eliminates 2, 5 in the rest of the box. This can't be 2 anymore. It's 1, which makes that 3, which makes that 2. 1 eliminates 1 here, so it's 4 and 1. 4 eliminates 4 here, so it's 7 and 4. Okay, remaining digits in row 2, I guess. We should, or column, let's box 2. It has to be 8 and 3. 3 can't be here because of 3 in the row, so this is 8 and 3. 8 eliminates 8 here, so it's 9 and 8. Remaining digits of row 2 are 1 and 7. This can't be 1 because of 1 in the column, so it's 7, 1. Remaining digits of row 3 are 4 and 9. This can't be 4 because of 4 in the column, so that's 9 and 4, which makes this 8 and 9 there. Oh, 2 eliminates 2 here, so it's 5 and 2. Remaining digits of column 5 are 6 and 9. Okay. We don't have anything there. Column 7 are 7 and 8. This can't be 7 because of 7 in the row, so that's 8, 7, which eliminates 8 here, so it's 9 and 8, which eliminates 9 here, so it's 6 and 9, which leaves that as a 5 and this as a 6. And that's how you solve this puzzle. Pretty interesting. Yeah, the logic on this was actually not that easy, but the execution was fairly easy, I should say, if you've done a decent amount of yin-yang puzzles. Yeah, I think I would classify this as easy too. The logic is a little bit... well, it's not that challenging thinking about it. I don't know. It seemed fairly straightforward, but maybe that's just me. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.